So the end of last week, we started talking about what it meant to be continuous, for a function to be continuous or continuous at some value, x equals c. And so the definition says, and I have it up partly, says let c be a real number that is either an interior point or an endpoint on the interval in the domain of f. We say that the function f is continuous at c if we can say that the limit as x approaches c of f of x is actually equal to f of c. The function is right continuous at c, or continuous from the right. So if we can remember, if we're looking at the limit and we're coming in from the right-hand side, we push this plus sign here. So c kind of looks like an exponent of a plus of f of x. And this would be equal to f of c. And then we would say that the function is left continuous. So if we're coming in on the left-hand side of c of f of x, and it would be the same value as plugging in c wherever we saw an x in the function. Okay, so this might be helpful because we might have, maybe let's say we have a square root function, right? This is the square root of x. Well, we have to be careful because it has to, values of x have to be in our domain. But notice here, so our domain in this case is x greater than or equal to 0. So this would be continuous everywhere from 0 to infinity. But notice that there's no left-hand side of x equals 0 because the left of x equals 0 is not part of the domain. And so this is where this would be right continuous. So in our case here, the limit as x is approaching 0 from the right of f of x is equal to 0. So we gave conditions on what has to happen in order to be continuous at some value x equals c. And so recall, we can show a function is continuous. Okay, so to show a function is continuous at x equals c, we had to first show that f of c exists. You got some value back. We had to show that the limit as x approaches c of f of x exists, which as long as we're not on the left or one of the endpoints of our interval, then basically in this case, then we need to show that the limit as x approaches c on the left of f of x is the same value as the limit as x approaches c from the right of f of x. And then the last thing that we had to show was that that limit as x approaches c, that value we got back is the same thing as what we got for number 1, plugging in c wherever we saw an x, that y value. There's some other theorems that are going to help us look at limits and seeing if a function is continuous at a value. So let me bring that up. Okay, so properties of continuity or continuous functions. Okay, so this says if f and g are both continuous functions at x equals c, so if f and g are both continuous, at x equals c, then the following algebraic combinations are also continuous. At x equals c. Well, if you have some function f plus or minus some other function g, well, we know f is continuous at c, we know g is continuous at c, so it doesn't matter if we add those two or subtract those two functions, this is also continuous. If you multiply some constant k times your function f, where k is equal to constant, then k times f is also continuous. The product, so if f is continuous and we multiply it times g, which is also continuous at c, then those are both continuous at c. The quotient, so f divided by g, we have to say that g of c does not equal 0 though. The power rule, so these are kind of like our limits, right? So we have f raised to some power n. F is continuous at c, then f raised to that power of n is also, you know what, I skipped a number, didn't I? I can count. 4, 5. Doesn't really matter what number they are, but. And so 6, following from that general power rule, the root is also continuous. Okay, so if I have the nth root of f, this is also continuous. We want to put on a little stipulation because we can't take the square root or fourth root, even root of a number if it's not positive. So if n is, little stipulation here, if n is even, then our f of c value can't be a negative number because that would spit back out an imaginary number. It has to be greater than or equal to 0. If it's odd, you can take a cubed root of a negative, you get back a negative. So we're okay if it's odd index, the root, that's called the index, then you're okay. The other one that's going to really be helpful for us are on the composition of two functions. So here's another theorem or rule. So this says if f is continuous, at c and g is continuous, at f of c, then we can say the composition of those two functions. So remember, right, composition of two functions, you put that little circle in between the two functions. In this case, we're doing g of f is also continuous. at C. So if you're a polynomial function, recall polynomials are always continuous. So pretty much we can break up our functions so that it's maybe a composition of polynomials and using those rules that we had before of a power or the nth root or the composition of functions. So for instance, let's look at an example where this would be helpful. I don't know why they're bringing in limits. Okay, so let's just look at this example. It says find the limit, and then are the functions continuous at the point being approached? So the example, let's say, is the limit as x is going to 0 of sine of pi halves cosine of the function tangent of x. Okay, so trig functions, not all of our trig functions are continuous. Sine is continuous, cosine is continuous. We have to be careful of the trig functions that are composed of the rational trig functions. So like tangent is sine over cosine. And so we have to be careful because tangent of x is not always continuous. We can't have cosine of x equals 0. Can't have 0 in the denominator. But if you look at your tangent function, it is continuous at 0, right? If I look at my tangent function, recall that the denominator cosine of x is 0 at negative pi halves and pi halves, the y-axis. And remember that we had asymptotes here. But I was just thinking of what the graph looked like, and it looked like this. So I'm okay and taking this into pieces. And so we're thinking of this kind of like a composition. So we're going to have sine of the limit as x goes to 0 of pi halves cosine of this tangent of x. But I'm using these rules of limits. So remember, I can take a constant times a function and pull it out front. So this is the same thing as sine of pi halves of the limit as x goes to 0 of cosine of tan x. And so I keep doing that. I really usually would not write this out like this. But this is technically what we're doing. We can do this because of the rules. And technically, this is sine of this thing. So maybe we should have brackets. So if we go into this most inner piece here, and we plug in 0 where we see an x, and it is continuous here. Notice that as we're approaching 0, as x goes to 0, our y value is also going to 0. So we have sine of this pi halves cosine of this limit, which is 0. So cosine of 0, we can evaluate. Cosine of 0 is 1. And we have sine of pi halves. So sine is your y value. If you're thinking of the unit circle and at pi halves, you get that 1. So this is equal to 1. Okay, so the limit as x approaches 0 is 1. And if we look at, if this was, let's say f of x was equal to this function, sine of this pi halves, cosine of tangent of x. And we plugged in 0, we get the same value, right? So simplifying that down, we also get 1. We showed that the limit exists, and we got 1. And that f of 0, f of that function at the x value is also 1. And so it holds that this function is continuous at x equals 0. You can write it all out again. It's continuous. And x equals 0. So composition of functions that are continuous is also continuous. Some questions on that?